Let's learn about ethers today. See, there are two types of ethers, symmetrical one and unsymmetrical one. Okay. Symmetrical, as in both sides, we would have same alkyl groups like CH3O, CH3 type. And if you have two different alkyl groups, that is unsymmetrical kind. Okay. Next, if you see the IUPAC and common names for various ethers, how would they go? Check. If you have CH3O CH3, it is generally called as dimethyl ether. That's the common name. And methoxy, methoxy methane, which is the IUPAC name. So you always read alkoxy as a substituent, this as a branch, and then the remaining part will be your root chain, which is main chain. Next, if you have CH3O CH3 here, this is a longer chain. So now this will become methoxyethane, which is IUPAC name, and it is ethyl methyl ether, which is a common name. What if you have like this? If you have it like this, then the numbering will go like this: 1, 2, 3. So that will become 2 methoxypropane, 2-methoxypropane, which is the IUPAC name, and isopropyl, isopropyl methyl ether, that would be the common name. Next, this is methoxybenzene, which is the common name, and sorry, which is the IUPAC name, and common name is anisole. Common name is anisole. Same way, this is ethoxybenzene, which is IUPAC name. Okay, and phenetol is the common name. Next one, if you notice, we have 1, 2 position to which there is an oxygen connection. So it is called as, okay, 1, 2 epoxy, 1, 2 epoxy ethane, correct? Which is generally used in old IUPAC name. Okay, while the new IUPAC name is based on the ring. So this is a 3-membered ring. A 3-membered ether ring is called as oxirane. This is the IUPAC name which we will be using. Okay. The common name is ethylene oxide, because there is an ethylene group here to which oxygen is connected. So it is called ethylene oxide, common name. Okay. For example, if there is any substituent, there are two ways to write it. The old IUPAC suggests that we can use this term as 1, 2 and 3 and 4. So it is like a butane to which 1, 2 is epoxy, 1, 2 epoxy butane. But this is the old one. The new one, which is generally accepted more, is using this as an oxirane, starting with the numbering oxygen. So oxygen, then the substituted one, then this third one, which means this would be 2-ethyl oxirane. So that will be the actual IUPAC name. Next one, if you go the same way, we'll write it as 1, 2, 3. So it is 2-ethyl 3 methyl oxirane. So that will be the name. That will be the IUPAC name. Old IUPAC name, I think you know the rhythm, what is to be written there. Similarly, 1, 2, 3. So now this would become 2, comma 2 dimethyl. Sorry, first alphabetically ethyl should come first. So E 3 ethyl and 2, comma 2 dimethyl oxirane. Okay. So remember that this is generally called as oxirane. If it is four-membered ring, we call it as oxetane. Okay. If it is five-membered ring, oxolane. Six-membered ring, oxane. If six-membered ring with two oxygens, it is dioxane. Okay, dioxane. Got it? These are the important ways of representation, everybody. So please go through it once quickly. If there is any problem, please let me know. Let's see preparation reactions. First one, the most common one which we have come across is Williamson ether synthesis. Basically, we generate an alkoxide, we react with R-X via SN2 mechanism to get this into ROR dash, ROR dash. Okay, so typically this R dash must be SN2 ready. So this has to be SN2 ready form. Got it? So for example, if at all I want to prepare this this ether, the best way to prepare is make an alkoxide plus react with CH3Cl or CH3X. This is the best way to prepare. Suppose if you have OCH2, right, CH3, then the best way to prepare is this one, Na plus CH3Cl. Likewise, if you have this way, now you know that because the vinyl group can never be made into an SN2 ready form. So in that case, O minus Na plus, this is the one which you need to take and react that with propyl chloride. Got it? Similarly, if I want to get phenyl with one more phenyl group here, so you know that phenoxide has to be taken as a alkoxide and then benzyl alcohol should be taken as the SN2 form. Okay. And if you want to get PHOPH or tertibutyl or tertibutyl or any form of uh, bridge positions here like this with phenyl, these kind of compounds cannot be prepared by Williamson ether synthesis because none of them would be SN2 ready. Okay, we have done this multiple times in alkyl halides also, alcohols also. I'm sure you could recall that. Next, if you have 1 degree alkyl halide with 3 degree or more carbon, generally it gives E2 with tert butoxide. Okay, that also we have seen, which means if you have something like a tert butoxide, even if you react with CH3, CH2X, the major product will be OH plus CH2 double bond CH2. This will be major product. So except for methyl, ethyl or anything above, tert butoxide will always look for elimination. Okay. The same role just as how we did for Na2O or sodium, the same thing can be done for Ag2O as well. Okay. Dry Ag2O provides O2 minus. O2 minus attacks on Rx as a nucleophile, removing this X. So we will get this as RO minus. So alkoxide is being prepared. So that will attack on the second mole of Rx. And that's how we'll get ROR. Okay, so this is how we generate ethers. Next, from alcohols. From alcohols, we know that directly we can interact with concentrated H2SO4, correct? So around 417 kelvins here, right? So that will be C2H5O and C2H5. Got it? And same goes with Al2O3 also up to 250 degrees Celsius, correct? You can have C2H5O, C2H5. Whereas in case if you operate concentrated H2SO4 above 473 kelvins, then ethers, I mean alkenes would be major product. These will be major product. And same way, if you have Al2O3 given, Al2O3 given with heat, which means this is more than 300 degrees Celsius, then alkenes will be major product. So ethers are very much temperature control cases. For example, if you have this ether here like this, sorry, if an alcohol here like this, if you want this to make into an alkene, correct, using concentrated H2SO4, so H plus is what it provides. So the lone pair would be attacking this H plus, giving OH2 plus. So that makes this as a good leaving group. That's when the next mole of the nucleophile will attack on this oxonium ion. So the lone pair will go attack here, remove water out, and thus giving us an ether form like this. Okay, right. This happens at around 423 kelvins or 400 and I mean 420, 417, 417. Okay, approximately 417 kelvins here. But if you have anything above, if you have something like 473 kelvins and so, in that case, elimination is more favorable. In fact, suppose if you have even 2-degree alcohol, correct, even at this low temperature, right, if you are making protonation to occur here, correct, if you make protonation to occur here, then the second mole of alcohol here, correct, would usually prefer elimination over substitution. So in that case, again, elimination is more favorable even at low temperature. So that means even if you're operating at 417 kelvins, then elimination would be major product. Okay, and you will get this uh, OH2 again. Correct? Clear? So usually you would notice that this oxygen will take away this H plus, water will go away from here, and double bond will be formed. So this is major product, and that's how it will keep proceeding. Okay, so which means this is concentrated H2SO4 to get into ethers. This is for simple, simple ketones, sorry, simple ethers like methyl and ethyl based alkyl groups. Okay, otherwise they will be expected to go for elimination. Clear? So please look into the preparation once quickly, right? So this is from alcohols, everybody. See, continuing with the reactions. The first reaction we just learned, this is Williamson ether synthesis. Second reaction is with diazomethane, right? See, diazomethane typically have this structure CH2 minus and N2 plus. So in that, how do we make the reaction? First, CH2 minus will take H plus from there, convert into CH3 and N2. Now it will become diazonium salt. Now as it attacks here, now we will get this as ROCH3 plus N2 gas like this. Okay, here. right? So that's how we can get the ethers. And second case, when OH minus will take H plus from here, RO minus will attack on the methyl. So you will get 2 moles of alcohol plus SO4 2 minus. So this is, sorry, 2 moles of ROCH3 and SO4 2 minus. Next one, here also OH minus will be removed, O minus will attack. So you will get anisole. You get this as anisole. Same thing will happen with phenol here. You'll get this as anisole here and 2 moles of anisole here. Okay. So whether it is alkyl group or aryl group, you will get the similar type of ethers in this case. Next is from alkenes. Alkenes, this is oxomercuration, demercuration. In oxomercuration, demercuration, first we'll get mercurium bridge like this, and it is the methanol which acts like a nucleophile attack on the more substituted side, which later on carried out by NaBH4 to make a substitution. So I will get this as OMe and H here. Okay. So the H which you are getting is from this NaBH4, and this methoxide is the one which is connecting here. Got it? This is a very typical mechanism we come across: alkenes, alkynes, alcohols, preparation everywhere, right? Same way, first we will make simple protonation here, Markovnikov addition, wherein methanol will attack as a nucleophile, generates OMe as the product, which is ether. MCPBA will first convert into an cyclic ether, in this case oxirane, from any peroxy acid. So any peroxy acid will prepare the same. Same is the case with dry silver in oxygen prepares a peroxy acid. Okay. These are from alkenes, which we have learned the same things for alcohols. For alcohols, we used to just make further hydrolysis. If we stop it here, they'll end up at ethers. Next, from hydrohalin. From hydrohalin, first in the presence of OH minus, that will take away this H plus and convert into this O minus, which will eventually give you ethers. Let me show the mechanism here. So first OH is there. OH minus will consume this H plus here by acid base reaction. Got it? Creates an alkoxide here as O minus. Internally, it can attack towards chloride to remove this, and hence we will get this as epoxides. So that's how we can get the hydrohalins to convert into ethers. Now, in case if they are opposite to each other, correct? In case if they are opposite to each other, then you know that the sigma star orbital of chlorine would be more easily accessible for this O minus. Hence, the product what you will report when both of them are axial direction is this one, which is an ether like this, cyclic ether. But if they are in this direction, this O minus attacking here, correct, and removing this chlorine becomes little challenging. Okay. So in such case, we will report one OH here and one OH here. So that means even though it forms an alkoxide, attack would be relatively difficult for it. Okay. That's why we will generally report this as ethers this way. Okay. Alcohols this way. Next. If you have sodium or NaOH that can consume H plus, that O minus can connect here. Check out the ring size: 1, 2, 3, 4, 5, 6. So you will get oxone, right? So this is oxone here. So that plus half of H2, because that hydrogen has been released. This is the product formation. Here, the same goes here. So we will get oxetane and here also we'll get oxygen, right? Now, notice the properties of ethers here. If it comes to ethers, because of these two alkyl groups, correct, the bond angle between them will be, increase drastically. So bond angle would be somewhere around 113 degrees. Okay. So which means which is much greater than that of alcohols and phenols. That's why the dipole moment will be lesser than dipole moment of ethers. Generally, ethers is lesser than, okay, phenols is lesser than regular alcohols. Okay, but still it is polar in nature, so its dipole moment is not zero. Okay, but it is less, and because it is less dipole moment, although it is polar, it would have low boiling point because there is no hydrogen bonding unlike alcohols. It is generally used as solvents because it is having sufficient volatility for almost all the organic compounds, and it is unreactive. And lower ethers are soluble in water, that includes dimethyl ether and methyl ethyl and diethyl ethers. And as the R increases, alkyl group increases, the solubility of alkyl groups decreases. Okay, next. If you notice the reactions here, check out the cleavage of HX here. See, if the pure water or aqueous solution is present where the pH is equal to 7, then you will not see any reaction happening here. Got it? Even in basic medium, you will not observe OH minus going to attack or remove this OR minus, because OR minus is a very, very poor leaving group, hence no reaction. So ethers, literally the straight chain ethers, simple ethers, are only reactive in acidic solutions. Hence, if you have ROR with H plus, this is the way it will form, and that's when it will entertain the nucleophile now to attack. So as the nucleophile attacks not to any of these alkyl group, the bond will be broken here. It will convert into an alcohol plus R and Nu. This is how the connections would happen. Got it? So guys, I hope you understood. So ethers are pretty much unreactive as long as it is aqueous solution or basic medium. In fact, basic medium is the reason why we use all the solvents, that is Cn minus, okay, RO minus or RS minus, got it? Or NH3, ammonia or amines, got it? Halogens, X minus, got it? Or N3 minus. They all are unreactive with ethers. They all are unreactive with ethers. That's the reason why in SN2 mechanism, typically for these reagents, we take ethers as the solvent, everybody. Okay. Now, I have given you a glimpse that it might be in SN2. Of course, here the reaction could be SN1 driven also. And that's what we will try to understand. So you can see literally in alkyl medium, none of these reagents will make any reaction. They all remain inert. Important term, that none of these will make any reaction. They will remain inert in the solution. Hence, ethers are taken as solvents here. Got it? Next. Now let's see how the hydrolysis works in ethers. So if you take cold and concentrated H2SO4, right? The minute you use the cold form, it will only make more like an acid-base reaction. You'll have ROR with protonated oxygen, and that will have a combination of HSO4 minus. Since the water content is less, there is hardly any hydrolysis observed. So this is where you will stop the reaction. Got it? So in cold condition, so think about protonation here. So H plus is been provided. So the lone pair present on oxygen will attack here, and that will make an oxonium ion here. And now we do not have any strong nucleophile to support. That's why you'll simply report as RORH plus and HSO4 minus. Got it? While if you have sufficient acid, that means it is acid catalyzed hydrolysis, which means we have now enough water content present in it. In such case, we denote it this way: H3O plus or H plus in water, dilute H plus, dilute H2SO4. Then what would happen? First, the oxonium ion will form, and now depending upon either of these alkyl groups, accordingly the behavior will change. What does that mean? Suppose if either of these R group, either this or this, any one of these R group is either 2 degree, 3 degree, allyl, benzyl, or if it is octet completed case or aromatic case, if it is becoming an aromatic carbocations, any of this carbocation, if it is able to form, then the reaction will drive via SN1 mechanism, which means carbocation will form first and then water will attack. If it is both sides being 1 degree or methyl, both sides either 1 degree alkyls or both sides it is methyl group. Okay. In that case, it will always favor SN2 mechanism. In that case, it is SN2 mechanism. Now let's notice the SN1 route here, everybody. How does this happen? So imagine if this R1 is at a better carbocation site. In that case, first you'll get R1 plus, because after protonation, this entire thing will come out as alcohol already, and then water will attack, and that's how the alcohol will form. Okay. If it is SN2 route, and suppose both of them are either 1 degree or methyl, then water will attack on the lower substituted position, open it up, and then you will get this as alcohols. Now focus more on the examples, everybody. If you learn the examples carefully, you will get a better idea. See, if this is methyl and methyl, definitely both sides we have very small carbon contents. So if you have dilute H plus added, protonation will happen. Now water, what will it do? It will attack on any one of the methyl groups. Bond will be broken and you will get 2 moles of methanol. What? If you have either one side we have 3 degree, then after protonation, actually now the bond will break onto this side. Okay, the bond will break onto this side and CH3OH will be separated, gives a carbocation which is 3 degree, and on that 3 degree now the water will go and attack here, hence getting us 3 degree alcohols. Now imagine if this oxygen was isotopic, that would be left over or that would remain with methyl, and this alkyl group will take the water content which is coming from solvent. Same is the case here. One side there is 1 degree, the other side there is 2 degree. So after protonation, you know that the bond breaking will happen on this end. Okay, the bond breaking will happen on this end. So this side you will get a carbocation, and that's where the water will go attack here, and you will get that as the alcohol. So if it is isotopic, isotopic will go with that lower or a smaller alkyl group positioning. Okay. Okay. Help. Got it. Next. If one side there is methyl, one side there is ethyl, obviously this is the less hindrance side. So first you do protonation, and now the water would attack on the less substituted side and makes through SN2 mechanism here. Okay. So if this is an isotopic oxygen, so it will go away with the higher or larger alkyl group here. Got it? Now last one, this fifth one is also very interesting. Notice this one. You need to always emphasize on the first carbon position, everybody. That should be 1 degree. Okay. So on both sides it is 1 degree. Do not see that, sir, iske baad bulky hai, so can we go for SN1? No. In such case also you should strictly follow SN2, which means first you do the protonation step, and from here after protonation step, correct? Let me just copy this one. Okay. So once you get this here, now you notice that first H2O will think which is less substituted side. Since this is a less substituted side, here the attack would happen. Bond will break on this end, and you will start getting the product as CH3 CH2OH plus this one with this OH here. Okay. Now, if it was an isotopic oxygen, it must have gone with this one. This is where the isotopic oxygen will appear. Clear? So I hope you got an idea like in which case what type of mechanism need to be followed. See the sixth case. Once there is a phenyl group here, phenyl group will constantly give a double bond character. Okay. Simple reason. See, there is an ethyl here, oxygen, and then phenyl here, like this. Now what you did, you know that this by nature it will have a resonance stabilization here, correct? So as it is, the proton is less available, but yet let's say you somehow manage to make a protonation here. So if you make a protonation here, correct, you would always have this O and one second. Okay, you will have like this proton here, correct, with plus charge here like this. But still the double bond will be always active here. Double bond positioning will always be active, which means the H plus will be less likely to be attracted here this way, and the double bond character will always keep the benzene to have this double bond character. So hence bond breaking is never going to happen between this oxygen and phenyl group. So once you get this positioning here, okay, so what you would do, you would never going to attack on the phenylic group. So you will always attack on the oxygen. So on the ethyl group. Now you would notice that only ethyl cannot be broken into a stable carbocation. So it will follow SN2 mechanism only, and hence you will get this as ETOH, and bond would be breaking from this end, and thus it is going to form phenol. So ethanol and phenol. So this is the product that you will get. So wherever you have phenol, so just notice that. Now this is another misconception. Look into this seventh case. This is also 1 degree. This is also 1 degree. So instantly we might think, okay, this is SN2. But notice this. I told you if there is any stable alkyl group, which is alkyl carbocation group, you should always split into SN1, which means first protonation would happen. So you would get ET. Okay, let me write here mechanism here. ETO with CH2 CH double bond CH2, which follows by protonation first, and then you would have to break this bond into ethanol and then get CH2 CH double bond CH2 plus. Got it? And that's when you get water to attack, and you'll get an alcohol. So basically you'll get this as ETOH plus double bond here with OH here. That's it. This is a product formation. That same is the case with eighth one, everybody. This is going to follow SN1 as well. That means the bond breaking will happen here. So if I write the mechanism, OE, first protonation would occur with CH2 and benzyl group here. This will break into ETOH plus benzyl carbocation. Benzyl is a very stable carbocation, and that's the reason you will report the product as benzyl alcohol plus ethanol via SN1 mechanism, and the isotopic oxygen will go with ethanol. Okay. Now, this I told you, here the first carbocation is not stable, isn't it? So since first carbocation is not stable, it will go via SN2 mechanism only. And through SN2, this is a less substituted side. So the attack would happen on this carbon position. So we will get this as ethanol here, like this, with tert butyl and alcohol here. And this is the isotopic oxygen. 1 second. So I hope 6, 7, 8, 9 cases are clear. Right. Let's check out the next one. Now, these are the cases where neither SN1 nor SN2 is possible. So, because you cannot break into stable carbocation, neither you break into, neither you can make an SN2 attack. So, none of these would be happening. So, all of these cases, everybody, you can see right from 10th till this 16th one, none of these cases will undergo hydrolysis. Okay. Now, let's check out this 17th one, which is very interesting. That is, one side we have a vinyl group. So this side we have vinyl group, and the other side we have, okay, normal alkyl group. In such case, how is the hydrolysis done? So please check it out. CH2 double bond CH O CH2 CH3. Now, when a proton is being offered, that means it is in acidic hydrolysis, in acidic medium, the lone pair is in constant resonance with this pi bond. So it is this carbon which has the ability to take H plus first. So you need to make sure the first protonation does not happen on oxygen, rather it happens on carbon. And then we get this CH double bond oxygen with positive charge and CH2 CH3, CH2 CH3. So this is in fact the first step, everybody. And then once you have that, you can check CH3, CH double bond O plus, CH2, CH3. Now, water would attack on this carbon position because oxygen is most likely to take away its lone pair back from the pi bond. As it happens, you will get CH3, CH, OH2 plus, and then we have oxygen, CH2, CH3. This is what is going to happen. And that will help in making an intramolecular proton transfer, which means the lone pair on this oxygen will take H plus internally from this position, and that converts into CH3, CH, OH, and then we have OH plus this side and CH2, CH3. This is what you would get. And once you have this compound, now notice the lone pair of this oxygen will insist on this carbon to break the bond with the other oxygen so that it can start forming a stable double bond character. So we will have C double bond OH plus plus CH3 CH2 OH. This is going to be formed. And of course, this eventually will convert into CH3 CHO plus CH3 CH2 OH as products. These two are the products. Okay. Now let's see how the isotopic oxygen is moving across. I'll show it with the color. Okay. So this is that isotopic oxygen. This is where the isotopic oxygen is. Here it is, and here it is, and here it is, here it is, and finally after breaking, it is forming at this ethanol position. So this is how the bond breaking will take place. Got it? So finally, you would be reporting these two as the products. Correct? Now, what is the shortcut here? See, the shortcut is where you have CH2 double bond CHO and we have CH2 CH3. Suppose if it is this is how the bond is, then what you do, you always break on the vinylic position, everyone, and always give OH on the left hand side and H on the right hand side while breaking. So what does that draw into? So that will make it into CH2 double bond CH with OH, and this is like CH3 CH2 OH, right? You know that this will undergo, enol will undergo tautomerism to convert into this aldehyde. Now you can see this is the isotopic oxygen which is coming with this one. So this is the shortcut, everybody. Acha, even if you have two vinyl groups on both sides, let's say I have two vinyl groups like this, double bond connected to oxygen, another one double bond like this. Even in that case, if you perform hydrolysis on two vinylic positions, you do this two times now. Break here also, you break here also. Okay. You would be offering one OH on the left and H on the right here, and H on the left and OH on the right here, like this. So the central oxygen, if it is nascent oxygen, sorry, if it is the isotopic oxygen, it will convert into an water form, and rest of the molecule will convert into this form, double bond with OH here, and other one will also be double bond with OH here, and the next one will become H2O. Okay, so this is that isotopic oxygen. So you notice that this will convert into an aldehyde form. Okay, and this will convert into an aldehyde form, CH3 CHO. So these are the products that you will report. Done. So please thoroughly go through once what is vinylic, how the vinylic mechanism works. Everybody, please check out. Let's do this question as an application. All you need to do is simply break it. Use that shortcut. How to break? Wherever there is vinylic side, you break that. That's all. So let's see this. So what we'll be doing? I will break this into enol here. Okay. And the other side I'll get HO this way. And this will get tautomerized to form ketonic group here and ethanol. That's it. That is a product. Same case here. You will get enol plus you will get enol on this end. Okay. But this enol will undergo tautomerism. The other one is an allylic enol. So nothing, no tautomerism will happen. You will just report as these two products. This one and this one as product. Here also, you break it into enol form. You will get this one plus on benzene side, you will get OH. Isotopic oxygen will be here. This side, it will get tautomerized to get keto form. Then simple cases, wherever there is an ether, wherever there is a vinylic group, break on that side, give OH to vinylic side. Next, what if you have to identify the hydrolysis of acetals and hemiacetals? See, by definition, acetal is an ether which is geminal position, which means on the same carbon position, if you have two ether groups, that is called acetal. If you have one OH group and one OR group, that is called hemiacetal. Either of the cases, if at all you do hydrolysis, they will end up getting into alcohols, and this part will convert into, this part will convert into an aldehyde, and these two parts will convert into an alcoholic form. Okay. Same is the case here also. You break it on this side, this will become an alcohol, and this side you will get into an alcohol and water. This will convert into water, which is H2O. Will convert into H2O. Correct? Now let me show you how does the mechanism work here. Taking one example, I'll show you the mechanism, how the hydrolysis work here. Okay. So let's say I have CH3, CH2 with, CH with OCH3 and OCH3 here. Okay. While you do, while we push proton, one of the lone pairs will attack on H plus here, and that will convert into an alcohol form CH3, CH, OCH3 with plus here and OCH3. The lone pair present on this oxygen will push here, and that will break the bond here on this side. So in such case, we will get CH3, CH with double bond OCH3 plus CH3OH. This is what you will get. And now, if you take this compound and then make an hydrolysis here, OH, once again, the lone pair will attack here, pi bond will shift onto this side, and then we will have this as CH3, CH with OCH3 and OH2 plus. Okay, this can be isolated, which is going to be hemiacetal. This is hemiacetal form, which can be isolated. Or if you continue with this to further hydrolysis, so the proton transfer will take place. The lone pair will take H plus from here. Just a minute. Let me finish. Okay. So in that case, you will get this as CH3, CH with OCH3 and H plus here and OH. Now the same logic will apply again. Lone pair from oxygen will push here. This methanol will come out of that. So it will convert into CH3 CHO plus CH3OH. Of course, this is plus here, which will lose out the proton from it and convert into CH3CHO. So now you can notice the final products here. One is acetal, the other two are methanol. This is methanol. So this is how the mechanism takes place. So whether it is starting from acetal or hemiacetal, hydrolysis will always lead to formation of aldehydes. What is the shortcut now? See, the shortcut goes like this. If you have any R, CH, O, R dash, and O, R double dash. Okay. So you break it on both sides here, everybody. This side also and this side also. And place OH on the left, H on the right. Here OH on the left and H on the right. And in that case, what do we get? Now you can see you get this as R CH with two OH groups here plus one R dash OH plus one R double dash OH. Now this group, because two OH groups are unstable, that will convert into an aldehyde. So that's how you will report this part as the aldehyde here. Easy. Okay, I give you the mechanism also. And if you learn the shortcut how to use the hydrolysis, that is more than enough. You can solve all of these questions. Got it? So any kind of acetal you have, let us do it quickly now. Okay. So if you want, just have a look at it, and then we can see all the questions of acetals and hemiacetal hydrolysis. Done. Now notice, see, this is hemiacetal, right? Because one OH and one uh, OPH is there. So you can break down here. Then as you break that here, you'll get this as CH3, CH, OH, and OH present here. Correct. Now notice this one. Once you get an OH here, because both side we have OH, correct? Any of the water could go, isn't it? So which means if you have it like this, that means this can go as water, or this side will can, I mean, this can go as water and this can go out as water. So chances of getting aldehyde with oxygen here will be 50-50%. So this will be aldehyde with this with 50% chances, and another aldehyde maybe without that oxygen also, that is also 50% chances. Okay, what is the other product? That is phenol, this one. Okay, next one. This time 100% you'll get only one aldehyde. This is 100% only this aldehyde, and 100% you'll get only one type of methanol, only this one. The rest will be water, normal water. Correct. This is the product. Next one, we get CH3, CHO. Okay, and same logic here also, because this water is coming out to be attacking on it, so that means this can have 50% of chances here, and CH3, CHO, this could be 50% and this could be 50%, right? And CH2OH, that will not usually have any of that oxygen form. Clear? Because the bond breaking happens on this position here. This is from hemiacetals. Okay, so again I'm writing these questions. Usually hemiacetal is a word when you have an hydrogen here, okay, with that alkyl group. Instead of hydrogen, if you have an R, we use the word hemiketal because it is a ketone based uh, uh, ethers. We call it as hemiketals. But general terminology is hemiketals or acetals are considered similar only. Okay, so this is also you can read it as hemiacetal or hemiketal. It's one and the same. Product is the same here. You break down here. So as you break it, that you will get it as ketone here. One will be phenol. Similarly, here also, you break it here. One will be ketone here. The other one will be ethanol. Same way, next one, you break down here. This will be ketone. The other one will be methanol. Okay. Now, you can make the acetal formations in terms of the, I mean, I'm doing the reverse reaction now. That is how to make the ketols. So, you can have a cyclic ketal also. That means when these two will attack here, correct? Sorry, check here. As you break this on this position, you will break down here. I'll get so as you break that here, you will get this part as alcohol and this part as aldehyde, and the other side you'll get this as CH3OH. So this is the acetal which I'm breaking. Same is the case here. I'll break this acetal here. I'll break this side of the acetal or hemiacetal. So I will get this side, you'll get alcohol, and the other side I will get an aldehyde, and the other one will be water. And same logic you can see breaking here and here with two sides alcohols. So I will get this side alcohol and this side also alcohol. At the center I'll get this as an aldehyde. Here also break it here, break it here. At the center you will get an keto form, and this is connected group, so it will have like this with OH and OH. This is the alcohol that is left over. Now here also you can see I will be breaking on this end, so we'll get OH here and OH here, and the central carbon, which is only one carbon, that will convert into formaldehyde. Now, if that oxygen is connected on all three positions, you have to break down on three sides this way. So we'll simply get 3 moles of formaldehyde. Rest all will be water. Got it? So this is how the hydrolysis works, everybody. Please check and make sure you are also done with the same breaking of bonds. Check it out quickly. Let's see the next ones. Here also, after bond breaking, let's do it together quickly. What is the product? You will write here a keto form like this plus 2 moles of methanol. Okay, oxygen would be definitely present on this position. Next, if you have benzene form here, you will have benzaldehyde and you will get alcohol like this. Next, here we can have OH plus CH3CHO. This is with vinyl positioning. Just now we learned. Same thing. This with vinyl group and ethanol. But you will not write enol as a product. Everybody, you always represent ketone as a product because they get tautomerized easily. So these are the products you will represent. Okay. I'm hoping that all of you are able to do the same. Next. Now let's see how does the reactions usually happen with HI. If you take concentrated HI, there are two cases we usually do. One is with cold conditions, the other one is with hot conditions. If you take ethers, react with concentrated HI, protonation is the first step. Then you get this oxonium ion. Then I minus, being a strong nucleophile, would like to attack on the alkyl group following SN1. Sorry, following SN2. And SN2 is usually possible as long as that carbon is 1 degree methyl or 2 degree. But if it becomes 3 degree, definitely it will search for the root of SN1. Okay, so it's very simple. SN1 is always the favorite one. SN2 is always conditional as long as that R group is methyl, ethyl or 2 degree. Okay. Now, if generally in the questions, concentrated HI is given, but the detailing of the temperature condition is not given, default you will take it like a cold condition. So in that cold condition, what is going to happen is first the oxonium ion will form. On both sides, you're seeing typically methyl groups. So definitely it will go via SN2 mechanism. I minus will go attack and you'll get CH3OH and CH3I. Got it? So this is what would happen. Now check out the second case here. Second case also, if you have ethyl group here with CH3 and plus here like this. This is oxonium ion and I minus will still attack on this position because it is less substituted following via SN2 mechanism. So what is the product you will report? Ethanol and methyl iodide. Check out on this case, we have ethyl here and then we have propyl here. So protonation would happen, and since it is secondary position, although it might be stable carbocation, still because imine is a stronger nucleophile, you will still favor SN2 mechanism, and ethyl iodide and propyl alcohol is major product that you will report. In fact, the other products will also come where you will have OH and this one, but these two would be minor products in this case. So especially in the second degree only you will report these cases. If both side we have ethyl and ethyl, both side you have I mean 1 degree, 1 degree. In such cases, you will only report one these products. The other products are not reported, but only in second degree these products are reported. But these two are generally given as major products. Next, if you have 3 degree cases, now the minute one of them is 3 degree here, then you don't have to think, you simply have to make it as SN1. So this is the stable carbocation positioning here. So protonation would happen first, bond will break to this side, you will get CH3OH plus tertiary carbocation. So tertiary carbocation is the one which will take the iodide, converts into this iodide and CH3OH formation. This is the product form. All good, everybody? Right. In this case also, there is no other option, but we have PHO, we have tertiary butyl group, protonation happens, bond would break, report this as phenol and tertiary iodide, again followed via SN2, SN1 mechanism. Okay, this is also SN1. Next, here we will get this as PHOH plus CH3 CH2I, but this time it will be via SN2. Okay, because this is not forming a stable carbocation, so I minus is expected to attack simultaneously. This bond is breaking, so it is SN2. Seventh case, this is benzyl. Benzyl is a very stable carbocation, so you will report via SN1 mechanism as PH CH2I plus CH3 CH2OH. Okay. Now, in this case, no reaction, no reaction, no reaction. Got it? Everybody, please check these cases quickly now. 4, 5, 6, 7. Check. Right. Please see the next one. What if you have concentrated HI in excess? See, having in excess or a hot condition is same. Hot condition. So either you write it as a hot condition or you write it as excess. See, basically this is the same reaction what we have done earlier. You choose SN1 or SN2 accordingly based upon positioning of alkyl groups. But the one which got alcohol, you have to convert that also into iodide. That's all. Okay. The one which got alcohol form, you convert that also into iodide. So all you need to do is, this is the shortcut you use. You break on both sides, you convert that into iodides. That's all. See the first reaction kind with HIXs, it will follow simple SN2 mechanism. Oxonium ion formation, I minus will attack, this bond will break, and the ethanol which is forming, that also you process via SN2 to give this as ethyl iodide. That's all. Okay. So whatever alcohols are forming, convert that into iodides. See here, same thing. You break down here, break down here. So ethyl iodide, benzyl iodide. Mechanism wise, obviously it will follow SN1 this time because you have a stable carbocation here. Benzyl carbocation is stable carbocation. So I'll report this one and this one as a product. Third one, we can see one side we have phenyl, one side we have ethyl. So on the phenyl side, we get it as PHOH, and the ethyl side we have CH3CH2I. Okay, here. So this is how you need to convert into these compounds. So I think the excess part is very simple. I hope excess wala case you should not have any problem. Excess or hot case, it's one and the same. Next, what if you have an anhydrous HI? This is given specifically. It is been mentioned that it is anhydrous HI, which means since there is no content of water whatsoever, SN1 is never possible. Everything will go via SN2 mechanism only. So you notice everything will be via SN2 only. For example, here, this 2, if you compare, this side it is crowded. So what do we make it? We make this as ETO and like this. Then protonation would happen here, correct? Obviously, now the bond breaking will not happen. So this ET which is there, we have this as CH2 and CH3. So now we would have this as I minus attacking on this position, bond breaking onto this position. So we'll report it as ETI plus tert butyl alcohol. That is the product you will offer. Same goes here also. Anhydrous HI is given. So ET is best, SN2 is best attacked on ethyl position in this case. So the product you will report is CH3, CH2I and PH, CH, OH and CH3. Although this was a very stable carbocation by the way and benzyl carbocation, but still it will not happen because it will favor SN2 over the others. Got it? Next. If you have both side phenol, definitely no reaction. Anhydrous HI, this will also will not make any reaction. Okay. Now, the same case, let me elaborate once here as an example. Suppose if this was the case, like this, with simply given as concentrated HI. In that case, you will do protonation here. Like this. And then you will break the bond onto this side, get a stable carbocation plus phenol. And then stable carbocation will get iodide on it. So you'll get I here. So these two are the products you will report. This one as well as phenol. These two are the products which you will report. But with anhydrous HI, no reaction. Okay. Got it? So easy cases. This is a table given just for you to remember in which case what will happen. If you have concentrated, by the way, concentrated HI is same as cold conditions here. This is hot condition here. And this is an anhydrous condition here. Correct? Right. I have given you some exercise questions here. Question 1, 2, 3, 4, 5, 6, 7, 8. Up to this, you would try it on your own. See in excess condition, hot condition, what cold condition, what are the products you will get. Okay. Now, notice this. What if you have been asked that how many moles of HI moles we are using to completely react with these ethers? So check out. In the phenylic case here, we'll get this as OH and OH here like this. And then we have this methyl converting into CH3I, 2 moles of CH3I. So which means you have to replace this methyls with 2 iodides. So X is 2. So here you have to replace that with 2 moles because this side it cannot be broken again. Here also it is X is equal to 2. But notice this third case. Okay, observe it very carefully. Both sides we have ethers. So first what do we do? You will break them into iodides here. So CH3I, CH3I, sorry, this is the left side one, right side one, and at the center you have OH and OH. Okay. Now this OH and OH will also be reacted with 2 moles of HI and convert into iodide and iodide. I told you that 2 iodides are unstable at the vinyl position. You will get a double bond again. So this double bond will again be reacting with HI to finally get this as iodide. So the products you will report is this one, ethyl iodide and methyl iodide of 2 moles. Okay. So now count the number of moles happened here. Initially we took 2 moles, then again we took 2 moles, and last I took 1 more mole. So total 5 moles of HI were used. Okay. Let's do the same thing in the second case here. On the phenylic side, we cannot change that OH into I minus because you cannot make carbon oxygen bond here. But on the other side, we got iodide here and iodide here. Correct? But these two iodides are unstable. So I2 will go away. Alkene will form. Again, you react with HI. That will convert into iodide. Hence, X in this case are 3. Because we used first 2 iodides to get this and 1 more iodide from here. In this case, because the both are present in the ether form, we cannot make any reaction. So X is equal to 0. Next case is very interesting again. Check out here. We will have OH and OH first with 2 moles of CH3I. And this OH will require again 2 moles of HI to replace both those OH groups with iodides. And again, these iodides are unstable, so it will give away I2. So you'll get double bond. That when you react with HI, we will get this as iodide here, right? So therefore, X is equal to 2 plus 2 plus 1. So again, 5 moles. Last one, check out how many we can get. See, first we have like this with OH, OH, OH with 3 moles of methyl iodide. So you already consumed 3 moles. Again, we require another 3 moles of HI to bring these iodides at 3 positions, 3 vicinal positions. Now, this kind of cases we already done in the last topic, polyhydrides. So here I2 will go away, double bond will form, and iodine will be left. And this will again react with 1 more mole of HI. You will get 2 iodides in this position, correct? And again I2 will be lost. You will get an alkene. 1 more HI will be reacted. And finally, you will get this iodide here. So this is a product that you will report 1 and 3 moles of this. Done. So X, if you calculate now, initially 3 moles, then again 3 moles, then 1 mole and 1 mole. So total 8 moles have been consumed in this case. Got it? So quickly go through 1 to 7. Check it out. If you have not done it, if you have not written it, please write it down. 1 to 2 seconds, check out how many number of HI moles we are using. Done. Now notice, what is Zichel's method? See, Zichel's method is to determine how many number of OMe groups are present in a phenolic ethers. For example, if you have this phenol, and I need to know whether there are 3 or 4 or 5, 6, how many number of methoxy groups are present. In that case, what we do? We add with excess HI. So we'll definitely get, if you have n number of methoxy groups, I will get n number of methyl iodides. And if I treat them with AgNO3 and heat it, these iodides, even if it is on the methyl position, will combine with silver to convert into AgI precipitates. And once you get precipitate, you wash it and measure it, weigh it and see how much is in grams. And then convert that into number of moles. Number of moles will be X divided by the molar mass. So these number of moles which are present should be same as the number of moles of methoxy groups here, isn't it? So therefore, number of moles of the entire molecule will be equal to N into weight by molar mass. So if the weight of this entire compound is given, right, and its molar mass is given to us, correct? Then using that two fundamentals, we can calculate how many number of methoxy groups are present. Okay, because a lot of times how this confuses us, that what if there is OH, methyl, methyl here, OMe here, OH here, methyl here, and OMe here. Okay, it appears like we have, 4 methyl groups, but methoxy groups are only 2, correct? That can be only determined using this Zichel's method. So that's why using this formula, we can always calculate what is the value of N. So X, W, and M will be given to us. Okay, so easy. So a lot of times these questions have been asked. So it's simply put the values given, identify how many number of methoxy groups we have. Now let's see what are the important reactions of this ethers. Okay, other than hydrolysis or other than the acidic reactions, what are the other general reactions which you will come across? See, if you react with O2, okay, when you react with O2, what is the product you will get? O2 means if you're exposing ethers, simple ethers to air, you will get this as, at alpha position, you'll get this as O, O, and H this way. So this is called hydroperoxide. Hydroperoxide. And this will be a slow process. Got it? But it is explosive. But this is explosive. And if you continue to do this here, got it? So we will have O, I'm giving you this as an example, OOH, which is forming, sorry, mechanism wise, this will be O dot first forming, O dot forming here, and oxygen on the other hand will take it as OO dot, and these dots will get terminated. HOO dot, they will terminate to form OOH. So this hydroperoxide is formed, and that is explosive in nature. Correct? So this is that termination step which I have written it here. Okay. Now, what if you have react with chlorine? With chlorine in dark conditions only, one chlorination would happen. If you have excess in dark condition only, 2 chlorines maximum can come on 2 alpha positions here. That's it. But if at all you have it in light, Cl2, H nu, in light if it is given, and excess it is given, in that case, all the chlorines, all the hydrogens will be replaced by chlorines. This way, chlorine, chlorine, CCl3. So this kind of questions will be asked, that how many number of hydrogens, chlorines are present here. number of Cl present will be equal to 6 plus 4, 10. 10 chlorides will be present here. Right. So this is with reaction with O2 and Cl2. Ethers can be tested very easily by using FeSO4 followed by SCN minus. Basically, if you have any hydroperoxide group, okay, of course, this hydroperoxide group is present, in ethers like this as OOH, correct? And that when you react with Fe plus 2, Fe plus 2 will oxidize itself into Fe plus 3. So this peroxide is used for oxidizing Fe plus 3 first, Fe plus 2 first. And once you get Fe plus 3, Fe plus 3 on reaction with potassium thiocyanate will convert into a red color solution. So FeSCN thrice as a complex, or you can write it as FeSCN2 plus as a complex. Any of these complex form you write down, they are all going to be red color solutions. So you would notice that there is a red color coloration observed on the ethers here. Got it? So any sample of ethers with hydroperoxide present with dilute H2SO4 followed by Ki. Here OOH in the presence of H plus, it will again convert into H2O2. H2O2 when you react with Ki in H plus, it will get iodine to get oxidized to I2, and I2 in starch appears blue color. That appears blue color. So that is also an indication that there must be an ether present which has some hydroperoxide present with it. So these two are the typical tests which we use to identify ethers. Got it? Next, reaction with acid chlorides. So lone pair here, I mean, ethers are generally less reactive, but if you have acid chlorides, the lone pair can go attack here, correct? This way and make the products. So that's what I have written here. So lone pair attacks, O minus will form, close it, chlorine will come out. And once you get ROR, then other chloride will attack and you'll get one as R dash, Cl and ester. So one of the R dash and Cl will come out here and the other R dash will connect into ester formation. Okay. The alternative reagent is zinc chloride and heat. It will give the same reaction. Well, if you have carbon monoxide, so O will attack on the carbon, right? And that would make it as C minus. On C minus, one of the R minus will get substituted. So that's how you will get this as ester. Got it? So these two are alternative reactions of ethers, everybody. So these are less likely to be asked, but just in case you come across this, you know that what is a product. Now notice reactions of oxirants. Very simple. Oxirants are reactive both in acidic medium as well as basic medium. Sir, why basic medium? Because of the ring strain. Because it is highly strained, even in basic medium, it will go via SN2 mechanism and open up the ring. So you notice that in acidic medium, first protonation will take place here and then the reaction will take place. So it will happen in two steps here. So first protonation, let me show you that here. First protonation and then attack of water or nucleophile present. This is in acidic condition. But the mechanism is SN2 only. This is SN2 driven. Or if you have it in basic cases, base will directly approach, break this bond, convert into O minus and OH here, and thereafter on hydrolysis, then you'll get OH and OH. Okay. So I want you to check out all the cases quickly, the same mechanism. So this is very important. All of them are SN2 reactions. But in acidic medium, protonation first, then followed by nucleophilic substitution. So first two cases, then lithium aluminum hydride, H minus first, O minus will form, O minus will take H plus from water. NaBH4, NaBH4, although it could have reacted, but the reaction is very slow, so you will not usually take it for NaBH4. RLi, very strong reaction, same problem. SH, strong reaction. C triple bond C1s strong nucleophile, MEBR strong nucleophile, MEO minus strong nucleophile. All of them will attack. On the other side, we'll get OH. Clear? This is ring opening reaction for oxidants, everybody. Next, regioselectivity wise, if you notice, this can be seen when you have an unsymmetrical cyclic ethers. So if you have these unsymmetrical cyclic ethers, correct. So first aluminum hydroxide, if aluminum hydride is there, that H minus would usually attack on the less substituted side following SN2 mechanism. So it will go via SN2 mechanism. So then O minus will be present on the more substituted position, and that would take H plus from solution, convert into alcohols. So this is a product that we will be reporting. This alcohol is a product we will report. Okay. Now, if one of the carbon is 1 degree and other one is a simple 2 degree, this side is 1 degree, this side is 2 degree, then also a regular SN2 is more favorable. Okay, then regular SN2 is more favorable. That means after protonation, water now has a chance to attack on this position and this position for different reasons. So this side it is less crowding, that's why SN2 is favorable. This side it is still favorable because this bond breaking is more easily. This bond breaking becomes more easy. Why? Because the methyl support is there, so that will help in breaking this bond more easily. That's why both side water can attack, and this is an experimental data. You just have to learn that only in the case of methyl and methanol, sorry, water and methanol, you will get 60% of this product where it is attacking on the left hand side and 40% will be on the right hand side. Okay, but if at all, if it is given with phenolic groups here like this, suppose if you have instead of methyl, if there is phenyl given and then H plus and H2O is given, got it? Okay, or let's say methanol is given. So in that case, proton will form first, plus charge, methyl, and then methanol will attack on this position, breaking this bond. So hence, we will get this as OH here, phenyl and methanol here. Okay, this is only major. So if you have phenyl, if you have any double bond support, allyl support, benzyl support, in such case, you will always have attack on the more substituted side. Okay, specifically only in this case when there is water and methanol and iodide also, sorry, I minus also. I minus also, you will get this less substituted as major product, more substituted as minor product. Now, if you have two methyl groups, I mean two methyls on this position, there is no question it will definitely follow SN1 type, which means the bond will completely break on this side in acidic medium and iodide will attack on this position. So you'll always give major product at more substituted side. This way, please check it out. So iodide, this bond is going to break after protonation. I minus will attack and you will get this more substituted product. Clear? So even with methanol, with HI, you'll always attack on the more substituted side. So you can notice that in all these cases, wherever there is acidic condition, you'll always attack on the more substituted side. So first case, protonation would happen, water attacks here. That is the first case. Second case, it is only base, so it will definitely attack on less substituted. Methoxide, less substituted. RMGX, less substituted. Lithium aluminum hydride, less substituted. SH minus, less substituted. This is also less substituted. This one, no reaction. And ammonia also less substituted. Okay, just in acidic condition, it will go in more substituted position. Next. Okay, epoxide as an electrophile. If you notice, benzene in the presence of AlCl3, we have done this in benzene chapter already. That EAS mechanism will take place, electrophilic aromatic substitution takes place, and you will be able to convert that into alcohols. Similarly, if it is with AlCl3, more substitute more substituted position is, more feasible for benzene to attack. So this side is the attack, and accordingly the product will form. Same is the case here also. If you have benzene here, more substituted position is one, it will attack as the oxygen attacks on this position. Done. This just for your information. Again, I have written it. Got it. So if you have two methyl groups, what is the product you can get? I think we have done this before. Yeah. No. If you have two methyl groups, you know which is a major product. Okay. Other reactions. See, with PPH3, what is the reaction you will see? PPH3 is a good nucleophile. So first you will have O methyl here. PPH3 is a very good nucleophile. It will attack on this position. Bond will break onto this side. So you will have this as O minus, and we will have this as phosphorus with P, PH, 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 and plus side. Got it? This is how you will get. Okay. Oh, sorry, one carbon I forgot. Like this. O minus is what you will get. And now this O minus internally will try to attack on phosphorus to get a four-membered intermediate like this. So O connected with phosphorus having P, pH thrice with plus charge, correct? And then that is connected here. Now that plus charge has gone because oxygen is supported with a bond. And now the bond breaking will take place. So because oxygen has more affinity with phosphorus, it will break here. This bond will break here. So what do I get? I will get this into an alkene, and phosphorus will convert into P double bond O with pH, pH, and pH. This is a product formation. Okay. This is a recent JEE question. Check out how this has been asked. If MeO minus is been first attacked, that will first attack here. Sorry, that will first attack here at, because this three-membered ring is a more strained position. So MeO minus will first attack here. Bond will break on this side. So we will get OMe. And on the next carbon, we have O minus. And then we have iodide here. And this oxygen will attack here, removing this iodide. So that's how you will get it as O getting attached here with methyl. And this has OMe on it. Okay. So this is a product formation. Clear, everybody? So again, I gave you some exercise questions here. These three, you would try it out with concentrated HI, excess, what would happen? Last thing is about reactions of anisole. This is very quick, simple cases. Check it out. Anisole is strongly electron donating group, highly activating and orthopara directing. So every time it will make an EAS, it will always offer para as major product. If you have excess, 2,4,6 will happen. Concentrated H2SO4, again para as major product, ortho as minor product. Friedel-Crafts alkylation, para as major, ortho as minor. And acylation also the same case here. Disonium salt, it does not make any reaction. Okay, OCH3 does not make any reaction directly on disonium salt. But if you have two NO2 groups on it, then it will make an EAS attack. That means if you have uh, OCH3 group here, so from this para position, it will directly attack on N2. And that's how you will end up getting this form. This is called a coupling reaction. And the product is called azodi. Okay, azodi compound or azobenzene. So this both side we have benzene group. So this is called the N double bond N is azo, and left side if you have benzenes, you call it as azobenzene form. Last thing is about Clayton's rearrangement. So where you have an ether which is in a allylic form with benzene. So please check it out. You have a double bond here with O and double bond here. Now what happens is the lone pair pushes here. Okay, we write the pi on the other side here like this. So now the pi bond from here will try to attack, this pi bond will move, and this bond will break. So in short, if you notice the reaction, how it is happening is oxygen is breaking a bond here, a double bond is forming here, and another bond is forming here, a double bond is losing out here, and another double bond is forming here. So this is a transition state that it is going through. So since it is a 6-member transition state, it is likely to happen this way, and you will get this as double bond O with double bond here, hydrogen here. Okay, double bond like this, and then it gets proton transfer getting into aromatic form. So you'll get OH and double bond here. Okay, so you notice one thing, since the carbon 14 is here, carbon 14 is here, so that got connected on this position now. So that carbon 14 will be here now. So you can see this is where it is. So that will become connected here. Okay. So another example, B case, if you notice, B case, if you notice, we have O double bond here. And suppose if there is methyl and methyl present on this position already. So, and carbon 14 is here. Correct. In that case, this will happen 2 times, everybody. First, you will get this double bond O methyl, and then double bond forming here. Okay. And from here, 1 second. So, give me. So from here, sorry, this is not benzene ring, double bond here and here. And from there, that will be shifting towards this side now again. So you'll get this double bond, sorry, double bond here, here, double bond O, methyl and methyl. And here there is hydrogen, which will help in getting aromatized. And that's how you will get double bond, double bond, double bond with OH, and like this one. Now notice one thing. If this was the isotopic carbon, that will be again coming outward only. So in this case, you will have 2 times this shifting is happening. So the second time again that carbon 14 will be outward. If it is one time shifting, it will be on inside, right? This is called Clausius rearrangement, everybody. Done with it? Here. So this is how much you have it for the syllabus from ethers. Got it?